Glycerin is made through a process called saponification. In this part of the video we will be discussing this process. The unrefined glycerin mixture is heated in section B by means of a coil. Due to heat, the fluid evaporates. With nowhere else to go, the fluid leaves through valve B1 into chamber A. Chamber A also has a coil and it is known as a superheater. The purpose of section A or chamber A is to maintain a constant temperature and flow so that free steam can flow back into chamber B. But what happens if there's an excess buildup of steam? Well, then it is relieved through valve A1 into the atmosphere. The rest of the steam flows back into chamber B through valve B2. When a constant temperature and flow is maintained, the fluid then leaves through valve B3 into the next section. This section consists of a series of condensers in order to compress the fluid. Once the fluid is compressed to a desired density, it then leaves through valve C1 into the next section, which is yet another compressor. The difference is the compressor in this section is orientated in such a manner where it is free to flow into chamber E. After a certain period of time, the glycerin mixture then condenses into a dense fluid and settles in the reservoir. We have now produced refined glycerin. This is a simple representation of the saponification process. If you are not happy with the final product in chamber E, the glycerin can also be refined once again and thus can be recycled back into chamber B. Also, something of note, the entire system is kept under vacuum conditions owing to a pump situated near section D.
So the fluid that we have chosen is glycerin. In the production processes, the fluid runs in pipes at an angle, right? So I'll be taking you through the mass and the fluid mechanics on how to get the average velocity and the volume flow rate of the pipes running at an angle. Relations for inclined pipes can be obtained in similar manner from a force balance in the direction of flow. The only additional force in this case is the component of the fluid weight in the flow direction, whose magnitude then becomes, in equation 1, Wx equals to the density times gravity times 2 pi times r, which is the radius, times dr, which is the thickness, times dx, which is the orientated coaxially with an inclined pipe in fully developed laminar flow, times sine times the angle, which is between the horizontal and the flow direction. In equation 2, this is the force balance. In equation 3, which results in the differential equation. Equation 4, following the same solution procedure, the velocity profile can be shown to be as follows. In equation 5 and 6, it can also be shown that the average velocity and the volume flow rate relations for laminar flow through inclined pipes are respectively. Okay, the only difference between horizontal pipes and inclined pipes is that in inclined pipes you have sine theta, and in horizontal pipes you do not have sine theta. For uphill flow, the angle is greater than 0. For downhill flow, the angle is smaller than 0.